But UI-TARS basically perceives the screen visually the same way we humans do. No more messing with hidden code behind the interface. It sees a screenshot, understands the layout, and works as if it's a user physically clicking and typing. This approach is known as a pure vision-based agent method. As you can imagine, it also means it can handle changes in the interface or platform more flexibly. But that's only part of the story. Another piece is something known as reflection tuning, or system-to reasoning, which UI-TARS uses for multi-step tasks and error correction. For instance, if it tries to install an extension in VS Code and something goes wrong, the model actually notices the glitch, checks if the application is still loading, and can correct itself accordingly. This reflection process allows UI-TARS to adapt on the fly. It might go, oh wait, that button didn't respond, let's try it again, or do a new approach. They've also run hundreds of virtual machines to generate all sorts of real-world tasks for it to practice on. Anytime it messes up, it notes how to fix the error, and that data feeds back into the model, so it gets better every iteration. This iterative feedback is basically how it polishes its performance. Now, how does ByteDance manage to train such a massive system? It's said they're facing some GPU export restrictions, so they apparently focused on all these algorithmic breakthroughs rather than brute forcing with giant computational clusters. They harness a ton of synthetic data, replays from user interactions, crawled tutorials, and so forth. Their pipeline collects screenshots from a broad variety of websites and apps, logs bounding boxes for each element on the screen, extracts the text that's displayed, and merges it all so the model can see how each interface piece fits together. Then it learns to unify different sorts of actions, like tapping on mobile or clicking on desktop, under one universal action space. The final end-to-end approach basically merges perception, the screenshot, reasoning, like what steps to take, memory, long-term, and action, mouse clicks, keyboard inputs, into one big model. And get this, the memory portion includes short-term memory for immediate tasks, like remembering which step it's on, and long-term memory encoded in its parameters, gleaned from historical interaction. That's how it can reason about, say, wait, I need to open the settings panel first, or we tried that, let's do a different plan.